Okay, so in this tutorial session, we will learn about star delta transformation. Okay, so what is it? What is star delta transformation? It is just a tool for combining resistors which are neither in series or parallel. So it is not always that resistors will be in series or in parallel. There are circuits that you come across at a point in time where no resistor can be seen or will be in series or parallel. So then what do? We use this transformation or this tool to help us do the conversion. So then we use this tool, and after transforming, you see that some of the resistors will be in series and some of the resistors will be in parallel. So then you can combine some of them and then you can find your effective resistance. So when we take a look at this figure A, you can see that neither of the resistors RA, RB or RC are in series or parallel. In parallel, we say that we should be able to traverse through a loop containing just two resistors. But let's see, taking this loop, you can see that we have RC, RD and RE, which means we encountered a third element. So we cannot say this is in parallel. We can't say that. It is neither in series or parallel. Let's look at this. We can also not say that when we take this loop, RA, you can see that RA, RB and RC, we are also not in parallel. And when we take this loop and we traverse, we can also meet this VS, which means we encountered another element. So we cannot say RB and RD are in parallel. Same applies to this circuit. We can see that taking this loop, neither of the resistors are in parallel, because when we move through this loop, we will meet a third element, let's say R4. So we cannot say these are in parallel. There is also a node between R2 and R3. We can't say they are in series. R2, R6 and R5 we cannot traverse through because we will meet a third element and we cannot say they are in parallel. So then what do? This star delta transformation that I spoke about earlier is a tool that will help us transform some of these resistors into series and parallel. So then how do we identify a star or a Y connection? This is a Y or a star connection. So how do we identify that? In star connection, one end of each resistor is connected at a point. That is the star point. This point here is the star point. Here is the star point. So we said that one end of each resistor. So we can see that RA, this is the end of RA, this is the end of RB, and this is the end of RC. They are all connected at one point here. And we can say that this is a star. Let's take a look at this figure 1.1. The same thing happens here. You can see that RB has one of its points here. RC also has a point here, and RA also has a point here. So we can say that this is a star connection. And how do we identify delta or resistors that are or forms a delta? Okay, so in delta connection, there are resistors, or let me say impedances, are connected end to end to form a delta. So let's see, this is R1, there's one end here, one end here. We have R2 here, there's also one end here, one end here. We can see R3, one end connected to the R1 here, and we have another point of R3 also connected to the R2 here. This is also a delta. So if you see this and you don't see this, don't say that this is not a delta, because from the definition we see the ends, they are connected end to end. So if you see, look at R1, you see that R1 is connected to this, and R1 is also having a connection in R3. When we look at R2, we can also see that R2 has a connection with R3 here, and this this wire, let me see. R3 also has a connection with R1 and R2. So if you see this, you should see that this is a delta connection. All right. So then, how do we transform a star into a delta, or a delta into star? When you take a look at this, let me say diagram, you can see a delta here, and I have a star in between. All right. So what if I want to change? A delta to star. Let's see what happens. This is the delta, and I'm changing it into a star, which means I should find the value of Rx, Ry, and Rz. So this is how we do it. To get your Rx, you should look at the two resistors that are sandwiching this Rx, that is R1 and R2. So they will multiply R1, R2, and then we will divide everything by the summation of the resistors around the delta. In this case, R1 plus R2 plus R3. The same scenario will happen here when we want to find Ry. When we take a look at Ry, we can see that the two resistors sandwiching Ry is R1 and R3. So we will multiply them. That is R1, R3. And then we will divide by the summation of the resistors around the delta. That is R1 plus R2 plus R3. The same thing will happen to Rz. This is Rz. The resistors sandwiching Rz is R2 and R3. So we will multiply them. That is R2, R3. And then we will divide by the summation of the resistors around the delta. That is R1 plus R2 plus R3. Right. So what if we want to change a star or Y? A star is also called Y, to a delta. Right. So this means we have to find R1, R2, and R3. So let's start with R1. If you want to find R1, look at the resistors facing R1. In this case, Rx and Ry are facing R1. So we will add them. That is Rx plus Ry. Then we will multiply them. That is Rx and Ry. Then we will divide by the resistor we did not use in the start. In this case, Rz. So it will be like this. So when I want to find R2, for that matter, R2 is facing Rx and Rz here. So from how we did this one, we will add them. That is Rx plus Rz. Then we will multiply them. That is Rx, Rz. Then we divide by the resistor we did not use. In this case, Ry. Similarly, if you want to find R3, the resistors facing R3 are Ry and Rz. So we will add them. That is Ry plus Rz. Then we multiply Ry, Rz. Then we will divide by the resistor we did not use. In this case, Rx. So having this formula, you can change either a delta to a star using these formulas, or change a star to a delta. So now that we understand star to delta transformation, we will solve some examples and try and use this tool and see how effective it is to know that. Right, so in this example, it says we should find the effective resistance between the terminal A and B in the circuit below. So let's say here is A and here is B. But we can see that this is a delta. This loop is a delta, and we have another delta here because the resistors are connected end to end to form this. So you can see 4 is connected here, 3 is also connected here, and this 2 is also connected here. So if we want to find the effective resistance, we can see that none of the resistors here are in series or parallel. So then what do? We use star to delta transformation. So since we have a delta here, we can put a star here, a star in the middle like this. So let's say here is X, here is Y, and here is Z. So from the transformations that we learned, we knew that if you want to find X, it should be the resistors sandwiching this X, and in this case it's 4 and 2. So we will multiply them, 4 times 2, and then we will divide by the summation of the resistors of the delta. In this case 4 plus 2 plus 3, which is 8 on 9. So we know that X is 8 on 9. We also transform Y. When we take a look at Y, we can see that 3 and 2 are the ones sandwiching Y. So we will see that 3 will multiply 2 out of the summation of the resistors of the delta. That is 4 plus 2 plus 3. In this case, we will have 2 on 3 ohms. And then Z. Here is Z. The resistors sandwiching Z is 4 and 3. So we will multiply them, 4 times 3, out of the summation of the delta resistors. That is 4 plus 2 plus 3, which is 4 on 3. So then that we have replaced this delta with a star, we will have to take this star and this delta out. So this is how it will look like after we transform it. It will look like this. And this is the star. So we have 2 ohm here, another 2 ohm, 4 ohm, and here was Z, and we had Z to be 4 on 3, and here was Y, and we had Y to be 2 on 3 ohm, and we had X to be 8 on 9 ohms. So from here we can see that 2 and this 4 out of 3 are in series. We can also see that this 4 ohm is in series with this 2 out of 3 ohm. So it will be like this. Our next circuit will look like this. So we can see that when we add 2 and 4 out of 3, we should get 10 on 3 ohm. And if you add 4 and 2 out of 3, we should have 14 on 3 ohms. So these are 2, and these are 8 on 9. So from here we can see that this 10 out of 3 ohm is in parallel with this 14 out of 3. So our total resistance, we can say that 10 on 3 is in parallel with 14 on 3, and the parallel combination of this and this will be in series with the 8 on 9, and they will all be in series with this 2 ohm over here. So RT, this should give us 2 plus 8 plus 8 on 9, which is 98 on 9 ohms, or in decimals 10.88 ohm. So we can see that we applied, or we changed this delta into star, and after changing it we saw that some of the resistors were in series, and after combining them we saw that they were in parallel and in series with this, and they are all in series with this. So we see how effective the star to delta transformation is. So in this second example, you have to find the effective resistance and also find the current supplied by the voltage source, that's the 10 volt here in the circuit below. When we take critical look at this circuit, we can see that none of the resistors are in series or parallel, because when we take this loop, we can see that we will meet a lot of elements, and in the rule we are supposed to meet just only 2 resistors, and we can see that they are in parallel. From here we can't, here too we cannot. The same thing applies here, the same thing also applies here. So then what do? We can see that this is a star. You can see this is a star, a very big star here, because all the resistors, that is the 4, this 4 and this 2, are all connected at a point here. So we can replace this star with a delta. So what will happen? Let's see. We'll place this delta here like this, another delta here, there should be another delta here from what we learned. So let's say if this is X and this is Y and this is Z, in this case we are changing a star to a delta. So what will happen? If you want to find Y, it is facing 4 and this 4 ohm here. So we will add them, that is 4 plus 4. Then we will multiply them, 4 times 4, all out of the resistor that we did not use, in this case 2. So this should give us 16 ohm. We can also find X. This is X. X is fixing 4 ohm and 2 ohm. So we will add them, that is 4 plus 2. Then we will multiply them, 4 times 2, all divided by the resistor we did not use, in this case this 4. So we should have 8. For Z2, the same thing. Z is facing 2 and 4 ohm. So we will add them, 4 plus 2 plus 4. Then we'll multiply them here and we'll divide by the resistor we did not use, in this case this 4. So we should get 8 also for Z. So then if we replace this delta with this star, let's see what will happen. Or let's see the new circuit. It will look like this. So after taking the star out, because we've replaced the star with the delta, you will see that this was a Y, and for Y we had 16 ohm, and this is it. For Z we had 8, and this is it. And for X we had 8, and this is it. So you can see that we've replaced this star with this delta. And from this we can see that some of the resistors are in parallel and some of them will become in series. Let's see, this 8 ohm and this 2 ohm are in parallel because we can traverse through this loop without meeting any other elements except 8 and 2. So we can see this and this are in parallel. The same thing also applies here. So now our new circuit will look like this. You'll see that we'll have this one over here, and we'll have this. Here will be the 16 ohm, here will be the 1 ohm, and 8 parallel 2 should give us 8 on 5 ohm. The same thing will happen here, 8 parallel 2, 8 on 5 ohm. Here, this is our 10 volts, this 1, this also 1. From here, very simple, we can see that this 8 on 5 ohms and this 8 on 5 ohms are in series. So we can add them, because when a current gets to this junction, the current that will flow through this 8 on 5 ohm will be the same current that will flow through this 8 on 5 ohm. So we can see that they are in series. So we can add them, and this should give us 16 on 5. 16 on 5. So our new circuit will look something like this. So here's our 10 volt, here's a 1 ohm, here's this 1 ohm, here's this 1 ohm. We have this 16 ohm here, and when we add it, 8 on 5 and this 8 on 5, we had 16 on 5, becoming a single resistor. So from here we can also say that this 16 ohm is in parallel with this 16 on 5 ohm, because we can traverse through this loop and we won't meet any other elements with the exception of these two. So this and this will also be in parallel, and it should give us 8 on 3. So the parallel combination of this 16 ohm and this 16 on 5 ohm gave us 8 on 3 ohm. So from here we can see that 8 on 3 is in series with this 1 ohm, and this should give us 11 on 3. This is the series combination of 1 ohm, and this should give us 11 on 3, and 11 on 3 will be in parallel with this ohm. So the total resistance here will be 11, and they will be in parallel with this 1 ohm, so like this. And the parallel combination of this 11 on 3 and 1 will all be in series with this 1. So our total resistance here should give us 11 on 14 plus 1. So our total resistance will be 25 on 14. That is 1.79. So the question also asked us to find the current supplied by this 10 volt. So now that we know our total resistance, it is easy for us to find the total current. That is the voltage over the resistance, total resistance. So it will be 10 out of 25 on 14, and this should give us 5.6 amperes.